Good morning, everybody. Welcome to another class. I sent a bunch of emails, I think, well, maybe two, out last night. It has the schedule for attendance for this week, and I might abandon the whole idea because it seems like even with increasing every time the number of people that get invited, there's still empty seats. So I kind of feel like I might be able to soon just say, come when you feel like it, and we'll be okay. Because we do have lots of space. If there's anybody nearby, you're welcome to come. But at the very least, for the rotation that I'm going to be putting out, if you had selected, I want to come every class, you can now come every class. Just don't even have to check. You can just come whenever you like. If you said every second class, the schedule is going to have you on every second day. So it'll alternate, one on, one off, one on, one off, pretty reliably. And then the other group, I've been sort of increasing the slots for people that want to come periodically. And that's all, like that's up to about once every 3 days. So that's not that different to me than once every 2 days. So what I might do is just have two groups, one that alternates day on, day off, and the other one that comes always. But if you ever feel like you want to come on a day that you're not booked to come, you can probably just come anyway. Like, look at all the empty seats, right? So anybody can jump in. And as I said in the email, kind of worst case scenario, if you show up and there's no seat for you, you could sit upstairs, which is nice and comfy, and attend virtually just from nearby. So it's not like there's a big cost if we end up filling up the room. I put up the grades as well for the oral exams, and you guys could find those okay. They were on the A1B1 site under grades, so you can, I don't even know how you do it from your side, but you can like check on your grades there, and hopefully, is this the only grade item that appears? I think all the other grade items are in, but I think I hid them all, so just wanted to make sure that because there's nothing there, they're just empty spots for now. I was pretty happy with how those went. People seem more nervous for those, I would say, than they would maybe normally feel for a midterm, which is understandable given that you're kind of on the spot, right? Nevertheless, I was very happy with how people did. People were very good, thinking on their feet, and generally speaking, I think people have a pretty solid foundation to build on from this point forward. So hopefully that wasn't too painful of an experience, and yeah, that's the last one of those, by the way. The rest of them will be normal ones, so no big worries there. Other than that, I don't think I have any other housekeeping bits of news for you, and we might as well get started talking about where we left off, which was talking about cyclohexane. And I brought today my model kit, and so I'm going to show you how to use your model kit today and how it can help us sort of understand the geometry of a molecule. It's a little bit more complex, like cyclohexane. And cyclohexane, we keep coming back to it because it is exceptionally stable because it has low, a low angle strain and low torsional strain. It's quite a stable structure. And for that reason, we find it all the time in naturally occurring compounds. Like sugars, we see these 6-atom rings all the time in sugars. And many, many other biologically important molecules as well. So biology recognizes that these are stable. Very stable organic substances, like let's say like cellulose, for example, is full of these kinds of rings as well. And it's an important structural building block in organic chemistry. It's a great way to put it. So on the screen here, I have a picture of the cyclohexane molecule. This is using the stick model that we talked about last time. And beside it, I have a picture of the globe. Hopefully you've all seen pictures of the globe before, unless you're a flat earther, which I hope you're not. But anyway, this is what the Earth looks like. We have an axis on the Earth that runs from the North Pole to the South Pole through the center of the Earth. And we have an equator, which is like a band that goes around horizontally around the widest part of the Earth as well. Right? And you're familiar with those features of our planet we live on. Okay, cyclohexane has hydrogens on it that come in two different types, or flavors, we can say. And we have names for these that mirror the terminology that we use for the Earth, equator and axis. So if you look at this, we have, I'm going to just use arrows here, and I'm going to draw those three hydrogens on alternating carbons are pointing straight up, and every other carbon has a hydrogen that's pointing straight down. Those 6 hydrogens, one on every carbon, we call axial. Why? Because if you position cyclohexane like here, like it is, they point straight up or straight down like the axis of the planet. Right? So we call these axial hydrogens. Every carbon as well has a second hydrogen that's pointing outwards, kind of horizontally from the ring. So you can see there's one here, one here, one here, one here, one coming out closer towards us and one going away from us. These ones we call equatorial. They point out like in the direction of the equator, if you can imagine this chair as being like a planet. So this is just another picture of the same thing, except I've colored in the left. The yellow atoms are all the axial ones pointing straight up or straight down. And on the right, we have all of the yellow ones as equatorial pointing outwards. Every carbon has one axial and one equatorial hydrogen. Okay? And they're all perfect tetrahedrals. They're all 109.5, the Vesper bond angles that you like to see for sp3 hybridized carbons. Now, one thing cyclohexane can do, remember we talked about ethane and we said it has multiple conformations. And you can spin one CH3 around as the other one stays fixed. And you can get staggered conformations and eclipse conformations and so on. And it spins around. Well, it turns out if you have a ring like cyclohexane, rotating around single bonds isn't that easy anymore. Because if you try to rotate a single bond that's part of a ring, you have to kind of twist the whole ring to do that. And so it's much more difficult to rotate single bonds that are within a ring. And if you build yourself a model kit, you'll see how this is the case. So I have a couple of the carbons. If you happen to have a model kit, I'm going to hold this up right here. So hopefully if you're on the camera, you can see it as well. You get a bag. Looks like this. And the bag is full of little kind of like black, lots of other colors as well. The black ones are supposed to be the carbons. What you can do is take 2 of these, and you can see where the little notches are inside. If you put 2 of those together and snap them, you can actually hear the snap, and you make a little tetrahedral carbon. So the idea is that the center atom is the carbon, and these are the 4 bonds that the carbon can make, and you can connect it to other carbon atoms just by putting like the narrow part of the bond into the hollow part of another bond like that. So this would be ethane, and you can see how if I spin this around with my hand like this, you can make a bunch of nice conformations. You can look at it by looking down the carbon-carbon bond angle, and you can see staggered, you can see eclipsed, staggered, eclipsed, and so on as you spin that around. But I'm going to continue this and build our cyclohexane ring. So cyclohexane has 6 carbons, 5 and 6, and then we just need to attach the 2 ends together. And you have what is a cyclohexane share. Can you see that okay, or is it like super tiny from where you're sitting? So if you have a kit, build one of these, just get a feel for the structure, see how you have on every carbon, there's 3 hydrogens that are pointing up, There's 3 hydrogens that are pointing down, which are axial, and every carbon has one that's pointing outward that we call equatorial. Sorry, equatorial. That's right. And what we're going to be doing now is looking at something called a ring flip. And a ring flip is a rotation that's available to cyclohexane. You can't just rotate a bond because, you know, it's not like ethane. If you start trying to twist it, you end up getting this, the bonds just won't move. So you can feel that. But what you can do, and when I say you, this is what happens in cyclohexane when it's in solution, is if you kind of grab one carbon in your hand like this, if you grab the opposite carbon in the other hand, you can kind of bend one up and one down. So you make another cyclohexane chair, but you sort of flipped it. You've taken one corner and you flipped it up and taken the other corner and flipped it down. Okay, so that's called a ring flip. And if you have cyclohexane in solution, it's doing this all the time. It's ring flipping back and forth. And you can feel, if you build the structure, you can feel a little bit of resistance before it snaps back into the next cyclohexane chair. So there's a small barrier to this, but the barrier is small enough to flipping that if you have a bunch of these molecules at room temperature, it can flip very rapidly back and forth. Now, an interesting thing that happens when you flip cyclohexane like this, when you do a ring flip from one cyclohexane chair to another cyclohexane chair, is replaces all of the axial hydrogens with equatorial hydrogens and vice versa. So I'll show you what I mean. I'm going to take, I need a couple of atoms here. Let's do a red one and a white one. Okay? So what I'm going to do is take my structure as I have it here. I'm going to put a white one on this position, and next to it, I'm going to put a red one on this position. So can you see this structure where I have the red and the white? Is the white atom on an axial or an equatorial position? It's axial, right? It's pointing straight up. So that's an axial position. How about this red one? Equatorial. So remember this, white is axial, red is equatorial. Now we're going to do a ring flip. You can pick any 2 carbons you want, pull one down and one up, as long as they're opposite each other. And I'm going to grab these 2 and I'm just going to flip it. Notice after I flipped it, the white one is now equatorial and the red one is now pointing straight up. It's axial. So you can flip it back again. Yeah, like that. White goes axial again, equatorial, axial, equatorial. So as it flips back and forth, and if you pick any 2 carbons and flip them, it'll flip the positions. It'll turn all the axial positions into equatorial positions and all the equatorial positions into axial positions. All right, so that's what I'm trying to show on this slide as well. You can see that in our structure. Basically, what we're going to do is pull carbon 1 up this way. We're going to bend it up, and we're going to take carbon 4 and bend it down, and you flip it, and all of the axial ones on the left that are labeled yellow become equatorial hydrogens that are labeled yellow on the right. Activation process is 45 kilojoules per mole. How much higher is that than the activation barrier for rotation of ethane? Do you remember that number by any chance? It was 12. So this is about 4 times higher, but 12 we said was peanuts. This is, I don't know, walnuts. It's a little bit higher, but still low enough that you can have very rapid flipping back and forth of cyclohexane, exchanging the axial and equatorial positions when this is present at room temperature. So it goes thousands of times per second, right? It's going very, very rapidly, back and forth, back and forth, back and forth. There's no difference between the 2 conformations in terms of energy of just regular cyclohexane, because you're just trading one chair conformation for another chair conformation. But if we look at a substituted one, in this case, we're going to look at fluorocyclohexane. So this is cyclohexane with 1 atom, and maybe in my model I have here, unfortunately it's red when the one on the screen is blue. But if you look at the chair conformation with only a single substituent group, a single side chain or single non-hydrogen atom, if you had this in an axial position, when you do a ring flip, you change its position so it's now in an equatorial position, right? So these conformations are not the same anymore. For regular old cyclohexane, flipping it doesn't change anything. But now, when you put something on there, it does. Because in one example, you have an axial fluorine, and in the other example, you have an equatorial fluorine. And guess what? It has a preference, which position it wants to be on. It turns out if you make fluorocyclohexane, you put it in solution, let it start flipping back and forth, like it will at room temperature. And if you were to freeze all of the atoms and then count how many had the fluorine axial and how many equatorial, what you'd find is only about 40% has the fluorine in an axial position. By the way, fluorine is super tiny. Not as tiny as hydrogen, but it's quite small. It's the smallest, next smallest atom next to hydrogen. In fact, you see this a lot in medicine. Carbon-fluorine bonds are extremely rare in nature, but they're very common in pharmaceuticals because medicinal chemists realize that you can swap hydrogens for fluorines and not really change the shape of the molecule because the fluorine is roughly the same size as the hydrogen. That way, if you have a target, a drug that fits a certain receptor, you can start replacing hydrogens for fluorines and change the electronics, change the polarity and things like that, without really changing its size, its ability to fit into a certain spot. About 60% of the time, the fluorine will be found in an equatorial position. This shows that this molecule has a small preference to put the fluorine in an equatorial position versus an axial position. Doesn't mean you can't have the other one. Obviously you can. 40% of the time it's in that form, that conformation, but there's a preference to have it instead equatorial. And this is pretty remarkable given how small fluorine is, that it has any preference at all. If you switch to methyl, and methyl may not seem that much bigger, but it's quite a bit bigger. Because remember, the way we draw it here, it's also got kind of this big electron cloud around it. The orbitals, remember. And it's a lot bigger than it looks like when you just draw the stick model. For the methyl, if you make methyl cyclohexane and let it flip back and forth in solution and froze all of the molecules out, made them stop moving, and then counted them, 95% of them would have the methyl equatorial, and only 5% has it axial. So what we see is that this preference for a side group to be on an equatorial position gets stronger and stronger the closer you, or the larger you make that group. Okay, so a non-hydrogen group prefers to be in an equatorial position. The bigger that group is, the stronger its preference. The more it does not want to be axial. Can we go bigger than methyl? Methyl's bigger than fluorine. What's bigger than methyl? Ethyl. Ethyl's a little bigger. Anything bigger than that? Isopropyl. I'll show you in a minute. Okay, so why does this methyl group prefer to be in an equatorial position? It's because there is an interaction called a 1,3 diaxial repulsion. It's called 1,3 because if you counted the carbons, if you counted this as carbon 1 and then just went around the ring, 2, 3, 4, 5, 6, we're looking at an interaction between a group on carbon 1 and a group on carbon 3. They're both axial, right? This one's straight up, this one's straight up. So it's diaxial, and it's a repulsion because this hydrogen has, you know, a 1s electron cloud, and this methyl group has a cloud like this. And they can get in each other's face right there. Okay, they can try to occupy the same space. This is that model again we looked at. Remember the Nerf balls where you're trying to squeeze or compress the Nerf balls into the same space? You can do it, but if you let go, they'll push apart from each other. There's strain there. Okay, same thing. When you put something big, axial, it will have van der Waals strain with other things that are also axial. In this case, hydrogens. Even though the hydrogens are small, they're repelling that methyl group, which destabilizes. It creates van der Waals strain when it's in the axial position, which makes it want to push over into the equatorial position where it's kind of sticking out and not bothering anything. It wants to, the bigger that group is, the more room it wants to have as well. So this picture is just trying to show the difference between fluorine and methyl and why the methyl has so much more diaxial strain than the fluoro. It's because it's bigger. Strictly comes down to size. It's got more atoms, more electrons. The fluorine, by comparison, is much smaller. So let's go bigger than the methyl. How about this big thing here? Look at that. That's called a tButyl group. A tButyl group is a carbon with a CH3, a CH3, and a CH3. It's called tButyl because we have 4 carbons, which makes butyl in this group. And the T, not because it's T-shaped, because it's not T-shaped, it's for tert or tertiary, because this carbon is a tertiary carbon. So we call this a tert-butyl group. We're going to use this group a lot in this course. This group, every time you see tert-butyl, the first thing that should come to your head is big. Okay, this is a big functional group. Organic chemists use it a lot to block certain parts of a molecule to prevent things from happening there. This tButyl group super does not want to be axial because it's gigantic. It will create so much strain with these little positions, the 1,3 diaxial positions, that it really does not want to be in an axial position. The preference at room temperature is 0.01% axial, 99.99% equatorial. Turns out there's a large barrier to doing a ring flip from an equatorial to an axial position. And so what we say is that if you have a molecule, if you have a cyclohexane group on there, something huge like this, basically it doesn't ring flip anymore. It always wants to have the tButyl group in the equatorial position. So this axial is basically unimportant. Right? It's so high energy, it spends so little time in that conformation that when we think about a molecule like tButyl cyclohexane, we only really have to consider this conformation. Cool. Okay, how do you draw cyclohexane? Because this is not something that's easy to do when you're first starting out, and it's believe me, I've seen a lot of abominations. And if you don't draw cyclohexane close to correctly, it's extremely difficult to get whatever I'm asking you about that compound correct. So I'm going to show you, I'm going to switch apps here. There's some steps written out there about what you need to do to draw it. But when you're drawing cyclohexane, I'm going to recommend you do something like this. You draw a line which is basically angled at a slope of like 30 degrees. And underneath it, we're going to draw a second line. So imagine we're going to draw a line that's parallel to that. That's the same length. It's going to be offset downwards just a little bit, maybe half a bond distance. But we're going to start, let's say, at the halfway point of the first line. We're going to draw a parallel line, the same length that goes down like that. Okay. So that's not so hard so far. We've drawn 2 parallel lines angled about 30 degrees from horizontal. Now what we're going to do is pick a point up here somewhere that's roughly equidistant from the ends of those 2 lines. And what we can do is join them. We're going to put one here and one here. We're going to do the same on the other side. One here and one here. That's our cyclohexane chair. Now, if you've drawn the chair correctly, every line, every bond, every carbon-carbon bond that you draw should have another line opposite it that's parallel to it. So if you notice this line, the first ones we drew are parallel. This line and this line are parallel. And finally, that line and that line are parallel. Next, every hydrogen is going to have an axial and an equatorial. Every carbon is going to have an axial and an equatorial hydrogen. So I find it easiest to draw the axial ones first. So if you look, let's say, at this carbon, it's got one that goes straight up, one that goes straight down on the opposite side. And then they alternate. The left one is up, the next one is down, next one is up, next one is down, next one is up, next one is down. So those are all the axial hydrogens in this molecule. Next, every carbon will also have an equatorial position, and the equatorial bonds will also be parallel to bonds 2 carbons away. So I'm going to start on the far right, and I'm going to draw one that goes up like this. That's going to be our equatorial bond, and that should be parallel. I'm going to change my pen here. This bond, and this bond should all be parallel when you draw them. You do it perfectly. And I'm not claiming to do it perfectly here, but I've got a lot of practice drawing cyclohexanes. There will be another one on the opposite carbon on the other end of the molecule that will also be parallel to that line, which will come out here. So you can see all these pink lines are parallel. Okay, what else do we have? We have this carbon here will have one that kind of comes out like that. Actually, I didn't quite draw that one very well. Again, this one is going to have parallel lines. So let's do orange. This bond will be parallel to this bond, will be parallel to this bond, will be parallel to this bond. All right, we are missing one more. And let's go with green. We will have one on this carbon coming out that way, this carbon coming out that way. That's parallel to this bond, and that's parallel to this bond. So this is hard to do on first crack. It can take some practice. I see lots of different, I would say, bad attempts at drawing this. One that I see which is common is people will draw it like this, which I call the bow tie, right? And the problem with something like this is I don't know where you're going to put your hydrogens here. I don't know like what it's supposed to look like, but it becomes extremely difficult to tell apart the axial and the equatorial hydrogens. And we're going to be doing reactions on cyclohexanes where it's really important whether a hydrogen is axial or equatorial. And you have to be able to draw it clearly in order for me to see that. The other thing which is bad is if you draw a cyclohexane where, you know, say this carbon is supposed to have an axial and an equatorial that look like that, some people will kind of just draw one and they'll draw it off in some weird angle like there. So it's not axial and it's not equatorial the way they drew it, and I'm not sure it's because they don't know which one it is and they're going to put it somewhere in between and hope I side with them, but it's got to be pointing in the right direction in order for that to be clear. We will be doing lots of examples coming up with cyclohexanes, drawing them, putting things in the correct positions, so don't feel like this is one and done. And when we come back to this in chapter 6, you'd be like, oh, thank God, I properly learned how to do cyclohexane chairs way back when. Okay, try this out. Get a piece of pen and paper. draw cyclohexanes until you can master it, because it'll be super useful down the road. There's an app on, at least on iOS, I don't know if it's on Android, I don't have an Android device so I can't check, called Chairs. It used to be free. I think now it's like $2 or something like that. And what this does is it basically gives you cyclohexane chairs. It looks like this screen you see here on the right. It gives you the top one, and then it does a ring flip, and you have to predict what it will look like, or where this methyl will go after you do the ring flip. So one type of question I'll be asking you is I'll give you a cyclohexane with groups on it, and I'll say perform a ring flip, draw what the ring flipped product would look like. Would you like to see an example of that before we move forward? Yeah, let's do an example. Okay. Here's what I'll give you, something like this. Draw cyclohex chair of left-hand structure. Both ring flipped forms. If this is on a midterm, I would word it more eloquently than that. But what we want to do is redraw this molecule as a cyclohexane chair. I already screwed up. Parallel. And I can draw these pretty quick. I didn't go through all the same steps that I told you because I'm good at this. And we need to pick a carbon. So this is the way I think about it. Let's say like this is carbon 1. I usually like to pick the rightmost carbon to be carbon 1. So we're translating this structure to that structure. And see how we have a bromine that's coming forward and a hydrogen that's going backwards. I like to think of the one that's coming forwards as being up, pointing up towards us, and the hydrogen that's back as being down. So down and away from us. So that carbon 1 over here will have an axial position and an equatorial position. If you look at those two positions on carbon 1 in our cyclohexane chair, one of them is pointing up and one of them is pointing down. Okay. So look at your structure above. Whatever is labeled up, put it on the up position. And whatever is down, put it on the down position. Okay. So that's one form. You don't have to draw in all the other positions. You don't have to draw hydrogens all over the place on the rest of the molecule. In fact, it's preferred if you don't. It's preferred if you only draw hydrogens and substituents on the carbons that are not CH2s, because it makes it clearer what's going on at those positions. By the way, you can see I picked carbon 1 to put the Br and the H. I could have picked any carbon I wanted in the ring. So what would it look like if I picked a different one? Well, let's say I picked this one instead. This one will have an axial and an equatorial there and there. This one I would consider up. This one I would consider down. So the up gets the Br hydrogen. Up doesn't mean axial or equatorial. It means if you look at the two positions, which one is closer to the top of the screen? That one's up and the other one's down. Okay, so we need to draw a ring flip form. It's an equilibrium. It's flipping back and forth, not like resonance. Resonance is not flipping back and forth, right? Resonance, it's electrons localized. This is atoms moving. This is definitely flipping between two different possible forms. So the way we do this is we draw, and now this takes a little bit of skill. We're going to draw the mirror image of that cyclohexane chair. There, we flipped it. We took this. I'm going to get a little pink pen here. This one comes up. This one comes down. The other ones stay steady, and we're going to go kapunk. We're going to move our thing, we're going to flip it. And then when we do that, what happens is carbon 1 comes down here, and we have a down and an up. The bromine is still up, the hydrogen is still down, but now it looks like this. We've moved the bromine from an axial position on the left to an equatorial position on the right. Which one of these is more stable? Left or right? Right. Why? It has the bromine in an equatorial position, which is preferred. Okay. So yeah, this is the best place to put that. I don't know what the percentage would be if you looked at this at room temp. It might be, I don't know, 15% the left one, 85% the one on the right. That's just a guess. I don't know what the real number would be. Bromine is a lot bigger than fluorine, so it'll be more skewed than 40-60. I don't know if bromine is bigger than a methyl. It's heavier, but methyl has like hydrogens that come out on bonds and stuff like that. I don't know which is bigger. Okay, so has anyone downloaded chairs just now? Did you find it? Do they charge for it? $1.49. Okay. Anyway, if you want to get like super good at this, I think it's a game, and the way it works, I think it gives you like a timer. And if you get one right, I think it adds time to your timer. So if you're quick, you can go like indefinitely. And then it'll go from 1 to then it'll put 2 groups, then 3, then 4, then 5, then 6. And I had a competition one year who could get the highest score in this app. And I think the best I could do was like 30 or something like that. But people were getting like 150, 160, like structures in a row. You get like 1 point for every structure you get right. So people got extremely good at this. If you're the kind of person that likes like kind of like mindless games, just to, you can become so good at this. Like you can do these structures, these sorts of questions, like the one I just did, super automatically after enough practice. If you want to add that skill to your repertoire, being super good at doing chair ring flips. There you go. Okay, so we're not done with cyclohexane by any stretch. We're going to spend a little more time looking at some different features of this ring. And before we do that, I just want to come back to our idea of isomers that we introduced way back in chapter 1, unit 1. We talked about isomers as being 2 molecules or 2 or more molecules that have the same molecular formula, right? And we specifically talked about a type of isomer called constitutional isomers. And we said constitutional isomers are ones where the pattern of bonding is different between the two. And I think the example we might have given was like CH3, CH2OH versus CH3, OCH3, right? One's an alcohol, one's an ether, different boiling points, et cetera, but they have the same molecular formula, which is C2H6O. The connectivity is different. You know, it goes carbon-carbon-oxygen on the top one, or the bottom one goes carbon-oxygen-carbon. The oxygen bonds to it in the 2 molecules. They're fundamentally different molecules, and we call this type of isomer constitutional isomer. There's a second one we're going to introduce now, and we're going to get into a lot of detail into this next unit, called stereoisomers, which are isomers that have the same molecular formula. You know, otherwise they wouldn't be isomers. But the bonding is all the same. Like all the same atoms are still bonded to all the same atoms. What's different between stereoisomers is their 3-dimensional shape. Okay, and we're going to look at cycloalkanes as examples of stereoisomers. What we'll learn next unit as well is that there are more than one type of stereoisomer. And this is the part, I would say, that requires pretty good ability to visualize things in 3 dimensions, and probably a part where having a model kit may be super helpful to some of you. I, by the way, went through my whole degree and PhD without ever owning a model kit, so I didn't feel like that was necessary, and that may be the same for you. I'm not trying to push these on you if you don't feel like you need them, but I've seen people really it kind of make the difference for them. So yeah. Okay, let's look at dimethyl cyclopropane. We're going to look at the smallest cycloalkane, 3 carbons. You can't have a 2-carbon cycloalkane, can you? No. No. I'm just like thinking, no, you can't. You need at least 3 to make a ring. And so let's put 2 different groups on there. Let's take 2 methyls, for example. There's 2 constitutional isomers of dimethyl cyclopropane. You can either put 1 methyl on carbon 1 and 1 methyl on carbon 2. So we call this 1,2 dimethyl cyclopropane, or you can put them both on the same, right? 1,1. So there we go. We have a dimethyl cyclopropane that has 2 constitutional isomers. We call them constitutional because the pattern in which they're bonded is fundamentally different, right? We have methyls on 2 different carbons on the left structure. We have 2 methyls on the same carbon on the right-hand structure. Fundamentally different molecules. But if we look at this one, there's 2 possible stereoisomers of this molecule. You can have the left structure right here, where we have the 2 methyls both coming forwards, both pointing towards us. Remember, these atoms, I mean, they're supposedly tetrahedrals. There should be 2 other bonds on each of these carbons. They're not quite exactly tetrahedrals because the severe bond strain here, angle strain, these are like 60 degrees. So the other angles are going to be bigger than 109.5. But this has them both together. This one has 1 forwards and 1 backwards, right? And if we look at those 2 structures, this is the one on the left, where you have 2 methyls. You know, this is the 3-dimensional stick model of that molecule. And you can see the 2 methyls are both pointing up. So we often call isomers like this that have 2 groups we're looking at. We say the relationship between those 2 groups is that they are cis, CIS. And cis just means they're both on the same side. Okay, they're together, right? You have this one, and they're both, if you look at the carbon-carbon bond they're attached to, they're both above it. They're both pointing in the same direction away from that bond. The other possibility is this one called trans. And you can see there's the carbon-carbon bond here. There's 1 up there and 1 down there. These are pointing in opposite directions. And that's what trans means. The word trans, or I don't know if it's Latin or Greek or whatever, it means across. Right? So if you think of the word Trans-Canada Highway, it's a highway that goes across Canada. So you can say that these 2 methyl groups that are here and here, they're across from each other. They're on opposite sides of this double bond. So I want you to think about this for a second. Look at this molecule and look at that molecule. Which of those do you think might be more stable? Cis or trans? What do you think? Trans. I heard a few trans. Anyone for cis? No, trans is much better. Trans is much better because these are relative. Remember, I'm drawing them as sticks, but they're these big kind of squishy clouds. And this one over here, they get in each other's space. What do we call that kind of strain? Yeah, that's van der Waals strain. So you can only imagine this strain will get worse if you put something bigger on there than an ethyl. If you had more carbons or you had, something else on there. tButyl, imagine tButyl, it'd be gigantic. You'd have a crazy amount of strain there. So putting 2 groups close to each other, generally speaking, creates strain, which makes the molecule less stable. That's destabilizing. So generally speaking, if you have a molecule where you have 2 groups next to each other, it's best to try to space them as far apart from each other as you can. So we can actually test the stability of these things by combusting them, putting them into a bomb calorimeter, measuring their heats of combustion. The one that has a higher heat of combustion will be less stable. These are isomers, so they both give the same products. So you can directly compare heats of combustion to determine relative stability. What we find is the cis is 3371 kilojoules per mole, 3366. So the trans is a little bit more stable by what? 5 kilojoules per mole. That's not a lot, you know. I wouldn't get excited about that. And, you know, 5 kilojoules per mole is tiny. Remember, rotating ethane is 12 kilojoules going from a staggered to an eclipsed. Flipping a cyclohexane is 45, right? So this is way smaller than a cyclohexane in difference. Breaking a carbon-carbon bond is like 380 or 350, depending on the bond. So like breaking a bond, this isn't anywhere close to that kind of difference. Question, yeah? Yeah, so the question was, for those online, would that kind of energy difference change how the molecule reacts? And the answer is absolutely yes. So maybe not in this particular case, or maybe not reactions we're looking at, but very subtle changes in energy between different conformations or between different isomers or so on can have a huge difference in how quickly these things can react, or whether they'll react at all. And we'll see some nice examples of this with cyclohexane coming up. Okay, let's jump back to cyclohexane, and let's consider 1,4-dimethyl cyclohexane. And so just drawing the bond line structure, we might draw something like this for the cis and this for the trans. The cis, they're both pointing towards us. The trans, one's forward and one's away from us. Either structure, those two methyls are super far apart from each other. So van der Waals strain between these two methyls is going to be basically insignificant, right? So we might not expect there to be any difference at all between them. Well, let's make them, throw them into a bomb calorimeter and see what we get for heats of combustion and therefore stability. All right, we do that. What we find is that the cis gives off more energy than the trans. Does that mean the cis is more or less stable? Right, the cis is less stable because it has a higher heat of combustion. It has more energy stored in it, more strain energy that it gives off when you burn it. So why is this the case? This may not seem super obvious just by considering what we did for cyclopropane. So what I'm going to do is I'm going to answer this by drawing it through. Rather than flip through the slides, I'd like to draw this one out. We have this versus the trans. So let's start with the cis. I would say that in both cases, there's hydrogens that are back, and their methyls are up, and the hydrogens are down. Let's draw our cyclohexane chair. And let's pick opposite carbons to be 1 and 4. 1, 2, 3, 4. Carbon 1, we have a methyl that's up. That's a CH3. And we have a hydrogen that's down. On this carbon 4, we have the up one is a CH3. Up doesn't mean axial up. Axial up just means up relative to the other thing on that bond. And a hydrogen that's down, right? So that's how you would convert the top structure to the chair form. Now that chair form can flip. So what we're going to do is draw the ring again, but we're going to draw a mirror image of it. Carbon 1 is still here. It has an up and a down, axial, equatorial. So carbon 1, the up is still methyl, the down is still hydrogen. Over here, the up is still methyl, the down is hydrogen. Of those two ring flip forms, which one do you think is better? Anybody have a thought on that? Yeah. So this one, someone said, because that is equatorial. That's true, but this one's axial, right? And the other one has an axial and an equatorial. So there's not an obvious winner here, is there? If the two things weren't methyls, if one was big and one was small, we'd prefer the structure where the big thing was equatorial. But these are the same thing. These are both methyls. So these are equivalent in energy. One is not better than the other. Let's look at the other one here on the right. This would be the trans. This one's up. This one's down. So carbon 1, carbon 4, carbon 1. We have a CH3 that's up, hydrogen that's down. Continue around the ring until you get to carbon 4. You can see the CH3 is down. And you get this. You can ring flip. And the methyl on the right is up, the hydrogen is down. Over here, the hydrogen is up, and the methyl is down. So we've done some ring flipping. Which one is best here, top or bottom? Bottom, big time. Because both methyls here are equatorial. Equatorial. So that minimizes that 1,3 diaxial strain, and it makes that much more favored over the other one. So overall, comparing all four of these forms, A, B, C, D, D is definitely the best because both groups are equatorial. C is definitely the worst because both are axial. And A and B are about equivalent. Well, they're exactly equivalent with one axial and one equatorial. So the most stable structure here is D. So that means that this is more stable than cis. Trans is better than cis for 1,4-dimethyl cyclohexane. That's because it has a conformation that puts both substituents in equatorial positions. And that's the place where they want to be and spend their time. Okay, we're still not done with cyclohexane. We're going to come back to it. We're going to do more examples and make sure that everyone is really firm with this understanding. But we're not going to do that today because we are out of time. So enjoy the rest of your day, everybody.
Thank you.